We're going to start talking about file systems and the whole issue of how do we manage storage on these devices. So basically, we always want to have some kind of persistent storage in our operating system implementation. And the easy reason why is because nobody wants to enter a program every single time they want to run it. And I think that if that was the case, then you would quickly run into people who say, I'm never using a computer again, or programs would be really short. But there's a lot of other reasons why we might want to have persistent storage. Configuration is a really huge one. Every Unix OS has a /etc with a lot of configuration in it, which is an obvious example. Then we have input data, output data, all kinds of other information that we might want to store persistently. Okay, we'd like this to last through process crashing or the system crashing. Databases are a great example of this because we want to be able to have data that stays around even if a program crashes and we need to be able to restore it somehow. Okay, so there's examples like that. So there's a lot of different forms of persistence. It's kind of funny because we started off the course talking about persistent storage, file systems, that kind of stuff. And now we're actually ending on the same note. So hard disks, very common. Solid-state drives, increasingly common. In fact, they're supplanting hard disks in many systems, unless you're shooting for like, let's say, like 2 terabytes or up. You can get a terabyte drive now on that's solid state for, let's say, like, what would you say, like $200 to $500 now, but they're still pretty expensive, and they get increasingly expensive when you go larger than that. So hard disks still have a very important role in these systems. Okay. Then you have a whole bunch of other ones as well, which we won't talk about. One of the things we skip in this class is how these technologies work. Okay, we spend more time talking about that in CS24 and definitely in 122, but in this class we don't really spend much time talking about these devices themselves. Okay. Now, if you have a program that needs to manipulate a really large data set, you sometimes run into the scenario where the data set is larger than system memory. And so that's another situation where a file system can be really helpful because you can load portions of it. You might be able to use virtual addressing. That's an obvious one, memory mapping the file. And then the OS will manage the loading of that data into the actual physical memory size. But a lot of times you just want to traverse the data set in blocks and manage that yourself. Okay. Sometimes you have situations where multiple processes should access the same data set. This, again, is a very common scenario in database systems where you'll have a set of data files that are manipulated concurrently by multiple programs. So how do we make sure that different processes can interact with that data concurrently? That's another problem that OSs have to solve. And then this is the biggest issue, I think, is that a lot of times the interaction with the disk is really slow, or the device, let's say. If it's an optical drive, it can be really, really slow. If it's a hard disk, then you're talking millions of instructions, maybe even tens of millions of instructions. If it's a solid-state drive, then we're talking hundreds of thousands to tens of thousands of instructions. Okay. So, but the nice thing is that they're block devices, and you'll frequently notice that OSs break these into block devices and character devices. So character devices would be like your keyboard, or yeah, that's probably the best example, because even network devices are kind of considered block devices. And then things like your solid-state drive, your hard disk are considered block devices, because reading multiple bytes is about as costly as reading 1 byte. Okay, so it tends to be that block devices are chunked into fixed-size blocks, and then the OS provides ways of reading and writing individual blocks. Okay, now the thing is user applications don't like dealing with blocks all the time. I mean, a lot of times we'd like to have an abstraction that it's just a stream of data, and so a lot of times you'll have a layer on top of block device interaction that is streamed. Okay. Now, here's other things applications don't want to care about. What parts of the drive or the device are unusable? Sometimes you run into that where sectors are bad. Spinning magnetic disks are kind of scary things where they'll have sectors that are marked bad, and then the OS just needs to know to stay away from them. Part of the difficulty of this is that sometimes those bad regions can grow. And this is one of the things that people have noticed about devices is if you have surface defects, a lot of times adjacent regions start to become defective as well. And so it's one of those things where you want to know about it so that you can replace the device relatively quickly. So that's one thing apps definitely don't care about. Remembering where data starts and ends on disk, and also data sets that may not be contiguous. And so basically you have this abstraction that you have a logical sequence of bytes. This is the abstraction that's presented by the operating system. We call it the file abstraction. They're logical units of information created by processes, and they tend to have an offset-based mechanism for access. So you have offset 0, 1, 2, so you can access each byte in sequence if you wish, or you can access them in blocks that are also in some logical distance from the beginning of the file. Okay, so pretty straightforward abstraction. The file system is the thing that presents this abstraction. Now, most of the time, OSs don't impose any constraints on what can actually go inside of a file. Okay, like I say here, the process is the one responsible for interpreting the contents. You may have a few distinctions, like old DOS and old Windows would make a distinction between text files and binary files. But the problem is, nowadays, text files can look like binary files because you have stuff like UTF-8 encodings or UCS2 or various Unicode encodings, so that now you look at the contents of the file and it may look roughly like text. You may see some characters that look like text, but then you'll see a lot of other characters that just look like binary data. And it's because we have so many character sets now that we want to be able to support. So OSs are moving away, and have been for years, moving away from this distinction between text files and binary files. Okay? You do sometimes have situations where the OS imposes formatting constraints, like your program binaries are a really obvious one. Remember the ABI, the application binary interface. Okay, so the OS will constrain what kinds of binaries can be loaded. And then you sometimes have situations, this is a fun one, when you were reading punch cards, well, the punch card imposed a constraint on what kind of data could be loaded. Okay? Like I say here, 80 character wide text files, it would be ASCII text files, and the output was always written to 132 character wide printers. So thankfully now we have devices where that's not really a constraint. But you do also have sometimes with embedded systems where they will impose constraints on data formats. Like old iPods, they've got to be MP3 files, and then later on other formats were introduced. Or your camera knows how to read and write image files and media files, and that's it. It doesn't really know how to interact with anything else. Okay, so you have various constraints depending on the OS itself. Now the way that we normally, and I know that a lot of this is going to be review, which is fine. We're just laying the foundation right now. But you'll have files referred to by name, at least in simple situations. This tends to be what end users prefer to do. Files frequently will have an extension as well. Current OSs frequently will hide the extension or allow you to not have it. But usually that's just the portion after the dot. So, or if you have multiple extensions, you may have a dot and then an extension and then another dot, like tar.gz would be a great example where you'd have multiple extensions. Okay. So the part before the extension is called the base name, and so you have a base name and then an extension that is supposed to indicate what kind of file it is. Okay. And so the term file name can either refer to the base name or the extension, depending on the context. Some OSs impose a constraint. So old DOS, again, would have 8.3 characters, and that would be the way that the file name was specified. That was always fun. Probably none of you have worked with an OS like that, I hope. But back in the day when I was using DOS, it was challenging to figure out meaningful names that fit in the 8.3 format. And when Windows started supporting longer file names, it was a big deal. It made life a lot easier. Some OSs care about case, some don't. Okay? Windows and Mac OS, by default, actually ignore case. So you would have those two names, capital foo and lowercase foo.txt, would refer to the same file. Some OSs make a distinction. Pretty sure Linux makes a distinction between those two names. Okay. OS X, you can actually change it so that it cares about case, but everybody says don't do it because it breaks a lot of software that expects case to be meaningless. So that's kind of a fun challenge to deal with. Okay, how do we organize these things? Well, you're all again familiar, I'm sure, with the concept of a directory or a folder. These terms are synonymous, but it's just a way of grouping files that you would like to keep together within the file system. And the idea is the directory also operates as a namespace. So within a directory, all the things, all the entries have to have unique names, but you could have the same name in different directories. So we have a simple namespacing mechanism here. And usually you have a root so that there's something that encloses everything else. And this also becomes the starting point for looking for other things. Now I mentioned that it's possible to have a file system without a root directory. This is weird, but it definitely happens. As an example, the Pintos file system has two special files, one that is the root directory of the file system, and the other that is a free space map on the file system. And each of those two things lives at a specific location. So sometimes you'll have a situation where the OS has specific things that it knows it needs, and instead of listing those in a directory, it just references them directly in some other way. So sometimes you'll have a situation where the OS knows to go look at a specific location. Okay? So, depending on the needs, you'll have various levels of complexity. Okay? Pintos is great because it actually is generalized. So you'll have nested directories. I think that's one of the things you have to build for the last assignment is you'll have to build nested directories and to arbitrary levels of nesting. And it's very similar to a real OS in that way. So you'll get some good experience. Yeah, there are OSs that have simple directory structures depending on the actual needs of the device. Now, I mean, you have stuff like my iPhone here. It's running a Unix OS, and so it's got a sophisticated directory structure. And anybody running Android, same thing. It's running a kind of Linux, so it has a complex directory structure. And so older phones, though, very simple older phones, a lot of times will have very simple directory structures. Maybe a root, and it'll just have files listed in the root. Digital cameras, same thing. A lot of times they'll just do like a two-level directory structure so that you can have groups of photos, but then you'll have just groups and photos. So we call these single-level directories. So you only have a single directory structure, and then everything else in the file system is a file. Obviously, that presents challenges with naming, and a lot of times when you have multi-user systems, you'll have multiple directory levels. Like I say, you need at least two because you'd like to give each user a place to keep their own files. But then you still need a root to control everything else or to hold everything else. Okay. So a lot of times these things are given names like master file directory for the root and then user file directories for lower levels. Okay. And then users can have as many levels as they want. Okay. So obviously these are pretty simple. We use much more sophisticated directory structures than these in real OSs. And so the way that most OSs work is that they'll actually maintain a graph of directories and files, where folders or directories are nodes that can have multiple things in them, and then files are leaves in these structures. Now you'll notice that in this example, it's a graph. It's not actually a tree. We can have multiple entries referring to a particular file. That's the way that most of these general purpose file systems work. Okay? So you still have a root at the top and then various subdirectories that enclose files of a certain kind. So /home is really common for user directories. And then I was mentioning before, /etc will be configuration. Bin will be where standard operating system binaries live. Okay? And so you can specify a path from the root to a particular file. That's the easy way of doing this. Notice in our example, we're starting with /root. A lot of times OSs will just leave off the /root because why? We know that that's where we're starting. Slash will kind of implicitly be the thing that denotes the root directory. So it would just be /home/user2/d. Okay, but obviously there's a lot of ways that this can be done. And one of the things that's kind of fun is the fact that there's a lot of different path separators that's been used through the years. I love how Multics would use a greater than because it kind of looks like an arrow descending down the various directories. Older Mac OS, like up to OS 9, would use a colon. So you would have A:/B:/C. Why not? And then obviously OS X, since it's a Unix-based operating system, uses / like most other Unix variants do. And the other thing is there's path separators like within a single path, and then if you have multiple paths, how do you separate multiple paths? And again, you see variety there as well. It's kind of a syntactic thing. So it's whatever the designers decided to do, no biggie, right? So you just have to make sure that you have something clear. All right, now processes will have a current directory. Again, this is something you probably have already noticed in how operating systems work, is that processes have a current directory. And as an example, when you log in, your current directory is your home directory, and so that's nice. You can just go ahead and work in there with no problems. The nice thing about having a current directory is it allows relative paths to become possible. So you can either say dot to mean the current directory or dot to take a step back from the current directory. And so if you were logged in as user 1, then you could access a file that user 2 has by specifying /user2/d. And this is just one example. There's a lot of other symbols that can be used, like tilde is frequently the current user's home directory. You can do tilde username, and that will be that user's current directory. And there may be other symbolic ways of referencing these things as well, depending on the operating system. But it's pretty straightforward. Now, obviously, just as a little detail, this is an example where the OS would have to decide, does it just allow any user to access any other user's files, or does it want to impose permissions? Right? Like if you try to do this on the CMS cluster, some things you can access and some things you can't. It depends on what the user has allowed. Okay? But there's permissions that you can grant and revoke to allow these kinds of things. Okay, does it make sense so far? It's pretty easy, right? I mean, this is all probably stuff that you're very familiar with just from your use of Linux. Okay, so this is what I was saying before. We don't necessarily want just anybody to be able to access stuff or modify it. So we frequently have what's called metadata. Metadata is data about data. So it just describes the data, and that is frequently where permissions are stored. There's a lot of other stuff too. So who created the file, who, or I should say when it's been created or when it was last modified. You may also have who modified it last if you want to audit that kind of stuff. Permissions, icon, so that if you have a graphical user interface, you can easily know what icon to show. And so there can be a lot of details that describe a particular file. Another example would be if you are storing media. So like MP3 files have a lot of metadata that can describe the contents of the MP3 file. Same thing with, that's what it's called, ID3 tags. And then if you have like JPEG files, you'll have EXIF data that describes information about the images. So you can get really sophisticated when it comes to the metadata that is associated with a file. And current operating systems know how to interpret this information so that they can show useful things to people about their files. Okay, let's see. Yeah, so you have this interesting thing. Notice that we have two C files, and one of them is shared between multiple directories. And so this is done through a mechanism called a link. Okay? Basically, you can think of links as being pointers, but on the file system. And again, you probably have encountered this kind of thing before. it turns out that there's a couple of different kinds of links in file systems. You can either have hard links, which you can think of it as a directory entry points to file data. And you can conceivably have multiple directory entries that point to the exact same file data. Okay? And so this presents an interesting challenge because obviously the data in the file that we're calling C on the diagram, we can't get rid of that data until we know all the hard links have gone away. So this is a great example of where reference counting appears all over in file systems, but this is yet another one where we can't get rid of that data until we know that the number of hard links is 0. Okay. This also gives you a really good clue as to why the delete operation in Unix, as far as the C standard API, is called unlink. We call it unlink because what we're doing is we're removing a hard link. And when that number of hard links hits 0, the file's data is actually reclaimed. Okay. Then we have symbolic links. Symbolic links are not specified by directory entries, but they're actually a separate file, and the file itself stores the path to the other file. Okay. So this is an example where user 1 has a subdirectory B, and they have a symlink or a soft, they're also called soft links. Sometimes I mix myself up, but they're called symbolic links, aka symlinks or soft links. And so it's basically a way of saying here's a file in another directory. Okay. Now, interesting details about this. Let me just go ahead and hide that because I don't want to talk about that quite yet. But when you have hard links, then a directory entry basically refers directly to the file. So a hard link is basically just like any other link in your file system. You can open that file, you can treat it just like anything else. Symbolic links, you have to know how to interpret them because you open that thing, you have to know to open the file. This tells me where the other file is, and then I go open that other file. So you can see that symbolic links require 2 steps, whereas a hard link requires just 1 step. Windows has symbolic links. I think they're files just called, what are they called? Does anybody here, do you use Windows? Do you use Windows? Okay. Yeah, I can't remember if it's like .sym or what, but it's very easy in Windows to tell when you have a symbolic link because the file just has a certain extension on it, and it's very clearly a symbolic link. Okay. Linux is a little bit more subtle about that. I mean, you'll see that it's annotated in a special way when you do ls with their appropriate arguments, and it'll actually tell you where it points. The other thing that's interesting about this is that hard links, if I want to delete C, I can just do that directly. In this case, in a symbolic link case, if user2/C is deleted, the OS won't stop me. It doesn't. You now have a dangling symbolic link. So user1/B/C would just be dangling, and you would know that you had a problem when you tried to follow the symbolic link, but you wouldn't necessarily know beforehand. Okay? So symbolic links are a little bit more wiggly than hard links. Hard links are a little bit easier to enforce. Okay, last point on this slide is that not all file systems support hard links. FAT is an example of a file system. You might be asking, why in the world are we talking about FAT? Well, it turns out that solid-state drives, not solid-state drives, but like the USB plug-in flash drives and a lot of the SD cards and so forth use a variant of FAT because like every OS knows how to access that. And so by using FAT on your USB flash drive or your SD card, you know it's going to be readable on whatever OS you use. Okay? So doesn't support hard links. Nobody really cares. Nobody expects that. But NTFS, Microsoft's OS, HFS, and all of the other standard file systems that are used for major OSs support hard links. So pretty good, pretty cool capability. All right, how do we actually manage the file data itself? So we say that files are presented with the abstraction that is just an unstructured but contiguous sequence of bytes. Okay, so programs are free to read and write whatever sequence sizes they want, and they're able to impose whatever meaning that they want. They could even seek out 1,000,000 bytes and then start writing. So you don't necessarily have to have that the reads and writes are contiguous. So the file system exposes various operations for programs to use. Create a file, delete a file, rename files, all of that is pretty obvious. And when a file is open, then it's going to maintain a position so that when the program reads or writes bytes, it occurs at a current position. And so this gives rise to the interface that you usually see for file systems to present. I can seek to a specific location that'll modify the current position. Sometimes you'll have OS's check, but a lot of times seeking doesn't actually involve any checks. You're perfectly allowed to seek way past the end of a file. And then you can perform a write or a read. And depending on the OS, you may have different responses for performing operations past the end of a file. If you write past the end, it'll typically extend. If you read past the end, you may get an error, or you may get some other behavior. And if you have multiple processes with the same file open, then each one has its own current position. So that allows, for example, one file to be reading one process to be reading one part of a file, and another process writing to another part of the file. Okay. So again, the OS doesn't really constrain programs. It's really only responsible for presenting this abstraction, and then processes are responsible for doing things intelligently. Now, that's obviously pretty crucial. Okay, let's see. Access patterns. So what are the common access patterns? Well, there's really basically just two, and they're pretty much exactly as one would expect. You either have sequential access, where you start at some point, maybe the beginning, maybe partway through, and you just scan forward. So we call that sequential access. Then you have direct access, aka relative access, aka random access, where you say, this is where I'd like to go, and you go directly to that location and read or write a specific piece of data. Okay? These are the two access patterns that file systems need to handle. And so this is sort of like the big challenge of supporting both of these efficiently. You'll notice that a lot of times file system design is oriented around those two problems, sequential access and direct access. Okay, so you have various file layouts. We're going to talk about we'll try to get through 3 today, and basically represents the bulk of what you see in operating systems these days. And you'll notice that some are good at sequential access, terrible at direct access. Some are good at both of these things. Okay. Yeah, this is the interesting one. If you don't have a way of taking, because remember the whole problem is I can seek, but the seek is from the start of the file. So basically the program says, I want to access this logical position, and the operating system has to take that logical position and map it to a sector on disk, or a block on disk, and then access that block. And so that's the big challenge. How do we perform that interaction efficiently? We get a logical offset, we need to map it to a physical block on disk. Okay, so since we can hold a lot of files at once, and we access these things on blocks, the file system has to keep track of where files live. And so a simple way of doing this would just be contiguous allocation. Okay? We assume that every file is always going to be contiguous, so we don't allow them to be multiple pieces. And we could have a really simple directory layout. We just remember where the file starts and how large it is, and we're done, right? Super easy. Obviously, the OS needs to make sure these things don't overlap, so it has to be careful about that. We need to be careful about free space management, but otherwise we just say every file starts at a block, and we know how large it is, and that tells us how many blocks it occupies. Okay. Indexing is easy, because all we need to do is take the position we want to read or the position we want to write. We divide it by the block size. That tells me which block from the start. We add in the starting block number, and we're done. right? So this is really good at both direct access and sequential access. Okay. That's good. The only problem is we have all kinds of issues with the fact that files are created and deleted. Okay? So we have external fragmentation issues. Remember that external fragmentation is fragmentation due to program behavior. So it's outside of the thing managing the resource. Okay? So after many creations and deletions, the expectation, unless they're all exactly the same size, or even we could say multiples of the same size, we expect that we're going to have a bunch of distributed little bits of files, bits and pieces, and we won't really be able to leverage those available pieces of space. One option is to try to compact. Okay, we could try to take the device and compact the data somehow so that we can sort of aggregate all of that free space. Okay. And you'll notice that this is similar to other circumstances that we've talked about already. But the only issue is a lot of times you need to make sure that the device is not usable, or you may have to restrict the usage of the data on the device while you do this compaction, because obviously if you're moving things and then programs are accessing those things, that can be difficult. That could be annoying to sort out, okay, at the implementation level. Ideally, the process still only sees its logical abstraction, but now you have a challenge that the file system is going to be really complicated to deal with this kind of a situation. Okay. Here's another one. Programs don't just stick with a specific size file a lot of times. I mean, maybe if you're writing images or something like that, once the image is created, it'll be at that size and that's about it. But a lot of times we have log files, and we continually add to the log file. So contiguous allocation doesn't work very well with that, because now I have a file whose size is growing, and I need to make sure I don't put anything in its way so that it can keep growing. That's really irritating. So contiguous allocation, as simple as it is, quickly breaks down. Now, you'll notice this because the file system that Pintos has starts out as a contiguous allocation system. So when you dig in assignment 6, you start digging into the file system implementation, you'll see that it has a block start and a size, and that's basically all that Pintos keeps track of for disk files. So that's one of the first things you'll have to change, is to allow extendable files. Okay, simple change to contiguous allocation is to basically support multiple contiguous regions. We call them extents. And that way you can start chaining extents together, and you can start working around this issue of being able to grow files, and also the other issue of external fragmentation. Okay. Now this is interesting. We start to mitigate the issue of external fragmentation, but another issue starts to show up called data fragmentation. Data fragmentation is when the physical layout of the data deviates widely from the logical layout of the data. Okay? That's the easiest way to think about data fragmentation. If the data is spread all out, or the physical and logical orders don't match, then on certain kinds of devices, you'll run into issues. Tape drives, you would really run into this issue. Magnetic disks, you also run into this issue, because seeks are the most expensive operation on a hard disk. And if the data is all spread out and all over the place, then the disk head is having to slew all over just to access the components of the file. Okay? So that's the idea of data fragmentation. You have data that is not contiguous or is spread out in such a way that the physical and logical orders don't match very well. Okay? Data fragmentation stopped being so much of an issue with solid-state drives, because solid-state drives don't have any seek cost. You know, the addressing to pull up a block of data is the same regardless of where that block exists. So data fragmentation stops being so much of an issue with solid-state drives. But as long as you have hard disks, which we will have for quite some time, you'll still run into data fragmentation issues. Okay. So this is CDs, DVDs, and tapes use contiguous allocation, shockingly. But if you think about them, all of these devices, just the hardware technology, is best suited to sequential access. CDs and DVDs and tapes all can do direct access, but that means slewing to a particular location. Like with tapes, you have to spin the tape just to get to a specific location. You have to scan past a whole bunch of data. CDs and DVDs are a little bit better, but it's still an expensive operation to go to a particular track on the optical device. Okay? They much prefer contiguous reads and sequential reads and writes. So contiguous allocation works well for those. A lot of file systems support extents, just sort of as a concept, but they employ a lot other sophisticated techniques. So I don't want you to look at these and say, oh, all these file systems suck because they just do extents. Well, it turns out that they do other things besides that, so they're quite clever. All right, linked allocation. So this is where we start getting a little bit more sophisticated. Basically, we have sequences of blocks linked together in some way. Okay? This is a really simple example. Our file system device is nice and small. Okay? We have 18 blocks of data. And notice that each block basically just has some part of it devoted to what's the next block in the file. Okay? To the point that at the last block, we just say, this is the end of the file. Okay? The directory entry will just say, here's the start of the file, and perhaps, if you want, here's the end of the file. Okay? And like I say here, this is good for sequential access, but it's not really good for direct access. And if you think about why, how would I get to logical offset 8,000? Well, with this, just given the information we have here, I have to take a whole bunch of steps. And I have to keep track of how far I've gone until I get to the block that lives on the disk that actually has the offset 8,000. So I have to walk through this. And since I'm walking through this, I'm doing a whole bunch of seeks and a whole bunch of reads. So this is not really efficient for direct access. This is only efficient for sequential access. Okay. So this is the downside of linked allocation, or I should say one downside. Another downside is that, well, I don't talk about this yet. I'll get to that in a second. But you'll notice here that since we allocate chunks of a single size, we basically don't have any issues with external fragmentation anymore. That's one of the things you always notice. If you allow the program to dictate the size of the storage unit, then you're going to have external fragmentation issues. If you dictate the size of the block and then just say, well, I'm going to allocate multiple blocks, then external fragmentation vanishes, but now you have internal fragmentation, and in this case, data fragmentation issues. Okay? Because if you have a block size, let's say you have a block size of 4 kilobytes and you have a 23-byte file, well, then you're throwing away a bunch of data. You're throwing away a bunch of space you could use for something else. Okay? Data fragmentation, same thing. The other thing that I wanted to mention is that a lot of times these blocks are powers of 2 in size, and people like to work with power of 2 size data chunks because then that works well with caching and other components of the system. Let's say that you're trying to design a system for virtual memory friendly, and your file system is throwing away a few bytes on each chunk just to say where the next chunk is. Well, now you start having complications, and your file system isn't going to play well with common usage. Okay? So you can see that these are some of the issues with linked allocation. Nonetheless, it's a pretty straightforward approach. Now let's look at another one, because if you take this and make a little change to it, then suddenly it becomes a really useful approach. And so that's where file allocation tables come from. Instead of having the sectors themselves or the blocks themselves say what comes next, instead we factor that information out into a separate table, and we call it the file allocation table. Okay? So instead of this picture, we take all the links and we store them in a table called the file allocation table. And so you'll have two tables. You have a directory table, which says this is the start and the end of files. And then you'll have another table Notice that we have one entry per block. So that's an interesting issue that we now have to deal with, one entry per block. And each block says, each entry says, here's the block that comes after this block. So the directory entry says file A starts at block 3. And so you go and look in the file allocation table. Block 3 says block 4 is the next block. You go to block 4, it says block 10 is the next block, and so forth. And you can use this to chase through the contents of the file. The nice thing is now each file block, each data block, only has to hold file data. It doesn't have to say what comes next. Okay, so we've actually factored out the details into a separate location. And so that's what is meant by a file allocation table. You'll have a special value to say this is the end of a file. You'll have another special value which says this block is available, so that you can easily use this as your free space map as well. You can use the file allocation table to tell what is not allocated. Okay, any questions? This is an important picture just because this is, I think everybody has come across a file allocation table file system at some point. This is what I grew up on because we had 5¼ inch, no, that's right, 5¼ and then 3½ inch floppy disks. And all of these floppy disks used file allocation table formats. And I remember as a young high schooler staring at hex editors, looking at file allocation tables directly, trying to figure out how it all worked. I won't go into the reasons for why, but it was cool. Okay, let's see. So yeah, this is nice because the file allocation table is small-ish. You can load it all at once, and so you can easily use that to figure out where logical offsets fall on the disk. Okay? And notice you get the whole file system into memory, so that makes it really easy. Now, the problem is, this worked really great for 5¼ inch disks. This is actually, by the way, there were two guys that designed this. One of the guys was Bill Gates, so he has done real cool things. The other guy, I can't remember his name. I want to say Mark McDonald, but I could be wrong. And but anyway, he was also an employee at Microsoft when they designed this. And it worked great for initial devices, which were small. We're talking like 360 kilobytes, if I remember correctly, and then 720 kilobytes for double-sided disk. That was amazing. So anyway, but they started running into issues with increasing device sizes. Okay. First thing that they ran into is that they didn't have enough entries in the file allocation table to correspond to each sector on the device. So now we have a problem that I have fewer file allocation table entries than I have sectors. So what do I do now? Okay. The original FAT system had 8 bits per entry. Okay. They had some weird thing where around the floppy disk you'd have 9 sectors, so good luck doing the math for that. You'd have 9 sectors around. And I can't remember how many tracks they had, but it was some limited number of tracks. So pretty straightforward to work with a file system of that size. But 8 bits per table entry, you could only have 256 blocks. And it was even a little bit less than that because remember that you would have to have one that meant end of file, and you'd have to have another value that would mean this thing is available. So maybe you'd only have 254 blocks that would be available for files. Okay? So that's where FAT16, FAT32 have come from, because what we're doing is devoting more bits per entry. And so you could say that the very original FAT format was FAT8, because that's all the bits that was devoted for each entry in the file allocation table. Okay, so that's that. Okay, so to solve this, basically file systems started using clusters so that each entry corresponds to a batch of sectors as opposed to a single sector. Okay? And this led to, it solved the problem, at least the immediate problem, but then we started running into a new problem, which is that you would create a file with 153 bytes, which I would frequently do because I'd write my basic programs and store them on floppy disks, and my basic programs were not that large, but you would notice suddenly it's consuming a lot of space because you have to allocate units of clusters. And so if you have 8 blocks per cluster or something like that, then even for your little tiny files, you're losing a lot of available space. That was pretty annoying. Okay? So you can see that internal fragmentation starts becoming a big problem with the FAT file system. Okay? And yeah, clusters could be 32 kilobytes, 64 kilobytes, not uncommon. And so this was something that became a pretty big headache pretty quickly. So this was DOS and then early Windows operating systems ran into this pretty badly. Okay. So this is why NTFS thankfully does not have nearly this problem with it. It has a much more sophisticated file system structure. But FAT always runs into this kind of basic issue. It has a few other issues as well. Like on FAT32, you can't have a file that's larger than 4 gigs. And again, you run into these kinds of constraints. Okay, questions? That's FAT. I think it's worth knowing about. Basically, other file systems, I'm just going to be able to introduce this because it's 154 now. But a lot of other file systems basically use indexes to files to solve a lot of the problems with both direct and sequential access. So notice now we have a directory entry which says, here's a file named A, and the entry that goes with that in the directory actually is the location of an index block. This also gives rise to the name inode. You've probably heard of an inode before. An inode is basically an index node for a file that describes where the file lives. So we've added a level of indirection. And the index node says, here's where all the data blocks are in the file. So this kind of becomes a per file allocation table, if you will. Just saying these are where the entries live. Okay. Now the nice thing about this is that direct and sequential access are fast. I just can cache this index block, and then I can do calculations really easily to figure out where to go in the file. So yeah, this is what I'm saying here. Position in index is the logical position divided by the block size. That gives me an index in the index block. I can just look up what sector or what data block that corresponds to. Okay. Also, I can put my metadata in there. The neat thing about putting metadata in the index block is, remember the whole thing with hard links? If I have multiple hard links to the same file data on the disk, then the hard link doesn't have to duplicate metadata. The hard link can just say, here's the file, and then the file holds the metadata, and it only appears in one place. So I don't have to worry about certain situations with metadata getting out of sync. Okay? So this becomes really nice. All right? So this is a really helpful thing. Now, like I say here, the obvious overhead is that you have this index block now. And that is a little bit more overhead than you might have in other formats, although really it's not that big a deal. The big challenge with this is just how do you deal with small files and large files in the same file system. Okay? You would like to, for example, avoid having multiple indexes chained together, because then you run into the same issue that you had with linked allocation. If I want to access something far along in the file, in a large file, then I have to walk through a chain of index blocks. That would suck. Okay? So you can see that an index block works great for small files, but for large files, now you have to start walking through multiple index blocks. Okay? So, yeah, like I say here, linked sequence. We'll just talk about this. I'm going to introduce, well, actually, you know what? It's Friday and it's 1:57, so let's go ahead and skip. I'm just going to go back here and say, study this, and next time we have class, then I'll talk about how we balance the concerns of small files versus large files so that we can deal with both of them relatively efficiently. And that'll give rise to this concept of multi-level indexes, which is the way that basically all modern operating, well, I shouldn't say all, because there's a really cool thing we're going to talk about next week with file system journaling and log-based file systems that approach this problem in a whole different way. But multi-level indexes has been a very popular approach to file system implementation for a lot of, like probably the last 3 decades or more. So we'll spend some time talking about that next time. All right, any questions? Okay, have a great weekend.